Hello and welcome to our Mathematics for Architecture lesson. Today I'm going to start by giving some information about this course, and then I'm going to cover the first 3 chapters of the material. I'm expecting to give approximately 12 classes. They'll be on Fridays between 6 and 8. Each lecture is going to be approximately 60 minutes, and then after that I'm going to answer your questions. We don't need to use the full 2 hours. If there's not full hours of your questions, then we can finish early. That's fine. Say that a lecture will be approximately 60 minutes. It depends on the material I want to cover that week. It's possible that I might take more than 60 minutes, or it's possible that I might take less than 60 minutes to cover the material that I want to. But on average, probably about 60 minutes. We can break the topics of this course up into 4 parts. First, I'm going to give an introduction. We'll cover topics such as sets, symbolic logic, numbers, Cartesian coordinates, etc. Hopefully, most of the first part of the course will be revision for you. Hopefully, you've seen most of this material in your high school. In part 2 of this course, we're going to be talking about the geometry of space. Part 3 is about finite mathematics, in particular combinatorics, which is the fancy way of saying counting, about probability, and we're going to talk about graph theory. And then finally, in the 4th part of the course, we're going to study a type of mathematics called calculus. And the way I'm expecting to break this up is the first 2 lectures will be for the introduction. I'll use 3 lectures to talk about geometry, 3 lectures to talk about finite mathematics, and then in the final 4 lectures, I will talk about calculus. I have written lecture notes for this course. You can find them in the course material section. And we're going to examine this course using both exams and homework. The homework, first of all, this will consist of some multiple choice tests which are on OLED. You will find these already available to work on them whenever you want. I'm going to set the deadline for all of the homework to 1 day before the final exam. So if you really want to, you could wait until January before doing the homework, but I think that would be a mistake for 2 reasons. First of all, you're probably going to be busy in January with lots of work from your other courses. You don't want to be having to do all of the maths in January as well. And the second reason is that most people learn mathematics by working a little bit each week, instead of saving it all for the end. So I would encourage you to try to do some of the homework every week or almost every week. There will be 1 midterm exam. I'll announce the date near the time. Week 8, perhaps week 9. This will be a classroom exam. And then after the end of term, there will be a final exam. And again, we're planning that this will be a classroom exam. Can anybody hear me? Okay, so it's probably not a problem on my end. If you can't hear, try fiddling with your settings, try disconnecting and reconnecting and see if that fixes it. Now, if this was a classroom course, you would be given 4 hours of lectures every week. And the general rule is that for every hour of lecture, you would be expected to study another 1 to 2 hours outside of class. So that means that you would be expected to study somewhere between 8 and 12 hours each week. For an online course, you're still expected to study the same 8 to 12 hours each week. We have 2 hours timetabled, so you're expected to study another 6 to 10 hours each week. What could that be? Well, that it would include doing the online homework tests every week or almost every week. I would think that you might like to re-watch recordings of these lectures. They will be available on both OLearn and on YouTube. You might like to read the lecture notes I've written or the lecture slides, which are all available to you. The lecture notes have lots of nice problems in. I would think that you would want to solve all of these. Most of these problems have answers in the back of the lecture notes, so you could mark yourself and check if you are understanding the material. In OLearn, we have a discussion board in which you can ask questions to me, or you can ask questions to other students to help each other solve homework tests or to solve the problems in the lecture notes. You might like to read some books about mathematics. I'm going to suggest 2 good books. And you might like to watch online videos from other teachers. For example, if you search for Black Pen, Red Pen on YouTube, you'll see that he has some nice calculus videos. Two good books for this course. These are not required purchases. These are completely optional. You might want to get these or you might not. A good book which covers calculus and geometry is Thomas's Calculus. This book doesn't include finite mathematics. The second book does include finite mathematics, college mathematics for business, economics, life sciences, and social sciences. You might like to try to find a copy of one of these. And before I begin, let me just point out that if you look to the bottom left, I have the slide number. This will give you a rough idea as to how far through a lecture I am. And if you're following along using the lecture notes, I have the current chapter written at the top. The first chapter of this course is about sets. What is a set? A set is just a collection of objects which is specified in such a way that we can always say if a particular object is in the collection or is not in the collection. For example, if A is the collection of 1, 2, 3, 4, and 5, then this is a set. B is a set containing apple, banana, and cherry. And C is a set which contains the letters N, E, I, and L. There's a symbol here. This means is in the set or is a member of the set. So for example, if B is the set containing apple, banana, and cherry, then we can say that banana is in this set, but date is not in this set. Each object in a set is called an element of the set. So the symbol on the previous page could be described as is an element of the set. If we had a set without any elements in it, then it's called the empty set. And we have a special symbol for the empty set. It's a circle with a line through it. Another symbol, this vertical line means such that. So for example, if I had the set X such that X is a weekend day, then this set must be the set containing Saturday and Sunday. If I had the set of X such that X squared is equal to 4, then this is the set containing -2 and 2. If I had the set of all of the people in the world who are more than 5 meters tall, then this is the empty set, because there's nobody in the world who is more than 5 meters tall. If every element of a set A is also in a set B, then we can say that A is a subset of B. And we have a symbol to write this. A is a subset of B. For example, the number 1 is in the right-hand set, number 2 is in the right-hand set, and the number 3 is in the right-hand set. We can say that the set containing 1, 2, and 3 is a subset of the set containing 1, 2, 3, and 4. Second example, banana is in the right-hand set, so the set containing banana is a subset of the set containing apple, banana, and cherry. These two sets could be equal. If we look at the bottom half of the symbol, it sort of looks like an equal sign. The set containing Neil and Sezgin is a subset of the set containing Neil and Sezgin. The universal set is the set of all elements under consideration. We're going to call this U. That's everything that we're thinking about on a particular topic. Now let's suppose we have A and B, which are both subsets of U. This rectangle denotes U. That's everything that we're thinking about at the moment. And A and B are contained inside this. The union of A and B is every element in A and every element in B. In terms of mathematics, we can write this as A union B is equal to the set of all of the elements E in the universal set U, such that E is in A or E is in B. We also have an intersection. That's the sets. That's all of the elements which are in both A and B. E is an element of U such that E is in A and E is in B. For example, the union of A, B, and C and B, C, and D is everything in the first set together with everything in the second set. So A and B and C and D. Intersection means everything which is in both sets. A is in the left set, but it's not in the right set. We don't want A. D is in the right set, but it's not in the left set. We don't want D. B and C are in both sets. So the intersection between these two sets is the set containing B and C. The complement of A means everything which is not in A. More precisely, it's all of the elements E in the universal set such that E is not in A. So for example, if U is the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's what we're thinking about at the moment. And if A is the odd numbers between 1 and 10, then the complement of A must be the even numbers between 1 and 10. We're going to need set notation later. Next, I want to talk about symbolic logic. A proposition is a statement which is either true or false, but not both. For example, grass is green. This is a proposition. This is in fact a true proposition. 2 plus 5 is equal to 5. I could ask the question, is this statement true or false? And you would be able to answer that. You could answer that it's false. My name is Neil is a proposition, and for me that is a true proposition. But what if I said, close the door? And I said, is it true or false? You couldn't answer that. Close the door is a command. It's not a proposition. Is it cold today? That's a question. It's not a proposition. You can't say it is cold. Is it cold today is true. You can't say is it cold today is false. And 1 is not a proposition. Is 1 true? Is 1 false? That doesn't mean anything. 1 is not a proposition. We can combine propositions together in different ways. For example, the symbol for or is this symbol, which looks a little bit like the letter V. So, for example, if P is the proposition, it is snowing today, and Q is the proposition, it is raining today, then P or Q is the proposition, it is snowing or raining today. Or another example using set notation. If M is the proposition X is in the set A, and N is the proposition X is in the set B, then M or N is the proposition X is in A union B. And let me just point out the or symbol and the union symbol sort of look the same. They're both open upwards. We can understand or using a truth table. We have P and Q. Each of P and Q can be true or false. 2 times 2 is 4. So we have 4 rows to this table. And the 4 possibilities are true, 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 false, false, true, or false, false. If P is true and Q is true, is P or Q true? This means either P is Q or Q is true or both. Yes, true. Let's go down to the second line. P or Q. Is P true or is Q true? Is at least one of them true? Yes, P is true, so P or Q must be true. Same for the third line. Is P true or is Q true? In other words, is at least one of them true? Yes, so this is true. And the final line, P is true or Q is true. At least one of them is true. No, that's false. P is false and Q is false. They're both false. Neither of them are true, so P or Q must be false. Now for another symbol. The symbol for and is this upside down V. So for example, if P is the proposition I am hungry and Q is the proposition I am sleepy, then P and Q is the proposition I am hungry and sleepy. Or an example using set notation. If M is the proposition X is in the set A and N is the proposition X is in the set B, then M and N must be the proposition X is in A union B. X is in A and X is in B, so X must be in the intersection between these two. And let me just point out that the AND symbol and the intersection symbol are also similar. They both open downwards. A truth table for AND. For P and Q to be true, we need both P and Q to be true. So line 1, are both P and Q true? Yes, true. Line 2, are both P and Q true? No, false. Line 3, both P and Q are true. No, that's false. Line 4, are both P and Q true? No, so we write false. The symbol for not is this. It's not quite a minus sign because we have a little tail on the right-hand side. So for example, if P is the proposition your teacher likes coffee, then not P is the proposition your teacher does not like coffee. If M is the proposition X is greater than or equal to 7, then not P, the opposite, so not M, the opposite of M must be X is strictly less than 7. A truth table for not is quite simple. If P is true, then not P is false. If P is false, then not P must be true. Not P is always the opposite of P. The symbol for if and only if, which I might abbreviate to IFF, that's if and only if, the first two letters in the final one, is this double-headed double arrow. And this means that P and Q are the same. For example, look at the truth table, line 1. P and Q are the same. Yes, they're both true. So this is true. Line 2, P and Q are the same. No. Line 3, P and Q are the same. No. Line 4, P and Q are the same. Yes, true. One more symbol is implies. That's a double arrow pointing to the right. So for example, if P is the proposition I am in London and Q is the proposition I am in the UK, then P implies Q. We know that London is in the UK, so if I'm in London, then I must also be in the UK. Let's look at a truth table for implies. And I'm going to use the London and UK example to explain this. First of all, if P is true, so I am in London, and Q is true, so I am in the UK, does this make sense? Yes, true. Line 2, imagine that I say I'm in London, but I'm not in the UK. Does that make sense? No, that's false. It's not possible to be in London, but not be in the UK. Line 3, let's suppose I'm not in London, but I am in the UK. Is that possible? Yes, there's lots of cities in the UK. I might be in the UK, but not in London. So this is true. And line 4, false and false. I am not in London and I am not in the UK. Is that possible? Yes. I might be in Istanbul, then I'm not in London, I'm not in the UK. So the bottom line is also true. There's another way to think about implies, and let's split this up into two. Look at the top half first. Implies says if P is true, then Q must also be true. Line 1, if P is true, then Q is true. Yes. If P is true, then Q is true. No. So then we write false. Go down to the bottom two. If P is true, we can stop right there. P is not true, so we don't need the rest of the statement. It's still true because P is false. P implies Q is only applicable if P is true. If P is false, then it doesn't matter what Q is. It doesn't matter if Q is true or Q is false. Now, we must only write P implies Q if both P and Q are propositions. This statement, which I'm going to draw a box around, is nonsense. The first part, integral from 0 to 1, 3x squared dx is equal to square bracket x cubed between 0 and 1. This is a proposition because this could be true or this could be false. In fact, it's a true proposition. But 1 is not a proposition. If a student wrote this, then they would probably be meaning equals just here. But if you want to write equals, then write equals. Proposition is only used, so implies is only used between two propositions. I also want to remark that if P and Q are propositions, then all of these ways of combining them, P or Q, P and Q, not P, P implies Q, and P if and only if Q, are also propositions. The converse of P implies Q is Q implies P. There's another way to change these around. The contrapositive of P implies Q is not Q implies not P. In mathematics, contrapositive is useful, but converse usually isn't. I'm going to explain why contrapositive is useful later today. So let's look at an example first. If P is the statement, it is raining, and Q is the proposition, I get wet, then P implies Q means if it is raining, then I get wet. The converse is if I get wet, then it is raining. That's not logically the same as P implies Q. The contrapositive is if I do not get wet, then it is not raining. Let's talk about some identities for symbolic logic. The first few are straightforward, and then as we get to the end of this list of 22 identities, they're going to get more complicated. P or P is equal to P. P is true or P is true. Well, if P is true, then the left side is true and the right side is true. If P is false, the left side is false and the right side is false. So these must be the same. P and P is equal to P. This is true for the same reason. If P is true, both left side and right side are true. If P is false, both sides are false. So these are the same. P or Q is the same as Q or P. P and Q is the same as Q and P. And if we have three propositions in brackets, it doesn't matter which order we do, with ors or ands. P or Q or R is the same as P or Q or R, and the same for ands. Let's go down to look at number 7 next. Not P or Q is the same as not P and not Q. We can take a not symbol inside the bracket here, but you would have to change or to an and. And rule number 8 is the same. If we take a not symbol inside the bracket, then and changes into an or. Nine and 10, think about numbers. Think about if we had A multiplied by B plus C. We know we can multiply that out to AB plus AC. Same idea is going here. Number 11, P or true is equal to true. True is something which is always true, and P might be true or P might be false. If P is true, the left side is true and the right side is true, because true or true is true. If P is false, on the left we have false or true. At least one of those is true, so this is all true. P or true is always true. For the same reason, I'll leave this for you to think about. P and false is always false. P or false is the same as P. If P is true, both sides are true. If P is false, both sides are false. P and true is also equal to P. P or not P. If P is true, then not P is false. So we have true or false. At least one of these is true, so true. If P is false, then not P is true. So again, at least one of the things on the left is true. So this is always true. For the same reason, P and not P is always false, because at least one of them is false. We never have that both P and not P are true. Not P is equal to P. Again, I think that makes sense. Similar to minus numbers. Minus 7. Let me write that again. Minus 7, we know is equal to 7. Likewise, not P is equal to P. The opposite of P is P. The final 5 are where it starts to get a bit more interesting. P implies Q, I'm saying is the same as not P or Q. I'll come back to that. P if and only if Q is the same as P implies Q and Q implies P. Okay, makes sense from the notation. Number 20, P and Q implies R is the same as P implies Q implies R. Number 21, if P implies Q and P implies not Q, then P can't be true. We must have that not P is true. And the final one, which is the contrapositive one, P implies Q is the same as its contrapositive. P implies Q is the same as not Q implies not P. Let's look at number 18. I want to prove that number 18 is true. Number 18 said that P implies Q is the same as not Q or, so not P or Q. And we can prove that this identity is true using a truth table. I start by writing all of the possibilities for P and Q. True, 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 false, false, true, false, false. That's everything that we could possibly have. And then we fill in the rest of the table. P implies Q. We can copy this from the previous table. Q is just a copy. True, false, true, false. Just copy that across. And I want a not P column. Not P is always the opposite of P. So because P goes true, true, false, false, not P must go false, false, true, true. Okay, now let's look at the right-hand part of the table. Not P or Q. I need at least one of not P and Q to be true. Q is true, so this is true. False, false. They're both false, so this must be false. True and true, true, true. True or true is true. True or false, at least one of them is true, so true. Now, what do we have here? P implies Q is the column true, false, true, true. Not P or Q is also the column true, false, true, true. These are the same. These are always the same. Because these are always the same, we must have that P implies Q is equal to not P or Q. On your first homework, I asked you to fill in a truth table like this to prove one of the identities. Let's do another one. Let's prove identity 22. Prove that P implies Q is equal to its contrapositive. So again, I have two propositions, P and Q. Each one could be true or false. 2 times 2 is equal to 4. We need 4 rows to our column. If we had something with P, Q, and R, then we would need to have 8 rows in our table, because 2 times 2 times 2 is 8. P implies Q, copy it from before, true, false, true, true. I need not Q, opposite of Q, and I need not P, the opposite of P. So whatever Q is, do the opposite for not Q. Whatever P is, do the opposite for not P. And now I want to look at the right-hand side of the table. Does false imply false? Yep, that's true. Does true imply false? No, that must be false. Does false imply true? Yeah, true. Does true imply true? Yes, true. So again, the tables are true, false, true, 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 false, true, true. These columns are exactly the same. So these things must be logically the same. P implies Q is the same as not Q implies not P. Before I finish this chapter, I have a little bit more notation to put in. The symbol for all is an upside down letter A. And the symbol for there exists is this backwards letter E. If you're trying to remember which is which, remember that the word all starts with the letter A and the word exists starts with the letter E. We'll use these later. The third chapter today, in the final 9 slides, is numbers. I want to briefly talk about number systems. We start with the first numbers that children are taught, the so-called counting numbers or the natural numbers, the numbers which go 1, 2, 3, 4, 5, 6, etc. These are the set of natural numbers, and we write this set using this special hollow letter N. So for example, 2 is a natural number, 2 is in N. 7 is a natural number, but a half is not a natural number. None of the fractions, the improper fractions are, so none of the fractions, the non-whole numbers are natural numbers. I say that 0 is not a natural number. There is some disagreement in the world for this. There's a minority of people in the world who want 0 to be a natural number, but most mathematicians in the world agree that 0 is not a natural number. And negative numbers such as -5 are not natural numbers. Okay, so what do we do with natural numbers? In the natural numbers, we can do addition and multiplication. What I mean is, if we take two natural numbers, let's say 2 and 7, we can add them together and we still have a natural number. We can multiply them together. 2 multiplied by 7 is a natural number. This is true for any two natural numbers. If we multiply them together, we still have a natural number. But we can't do subtraction in the natural numbers, because sometimes if we do natural number minus a natural number, we get a number which is not a natural number. So what do? What did humans do in our history when we encountered this problem? We invent new numbers. And the numbers which humans invented back in our history are the numbers which are now called the integers. That's all of the natural numbers and all of the negative numbers and 0. We denote the set of integers using this hollow letter Z. Why is it Z? It comes from the German language. In Z, we can do addition, subtraction, and multiplication, but we can't do division. For example, take two natural numbers, add them together. So take two integers, add them together, we still have an integer. Do integer minus an integer, and we always get an integer. We can always multiply two integers together to get an integer, but we can't always do division. Yes, we could do 4 divided by 2. That would give us an integer, but 3 divided by 4 does not give us an integer. So what do? What did humans do in our history? We invent new numbers. And the numbers which we invent are the fractions. We invent numbers of the form a divided by b, where a and b are integers and b is not 0. This set is called the set of rational numbers, and we use the notation Q, which comes from the English word quotient. So, for example, 0 is a rational number, 1 is a rational number, 3/4 is a rational number, 100 divided by 13 is a rational number, -4 is a rational number, 0.12345 is a rational number because we can write this as a fraction. This is the fraction 12,345 divided by 10,000. But some numbers we can't write as a fraction. Square root of 2 is not a rational number. We can't write this as a fraction. And pi is not a rational number. Anyway, what can we do in Q? We can do addition, we can do subtraction, we can do multiplication, and we can do division, as long as we're divided by a number which is not 0. So are we happy now? Do we have enough numbers to be able to do mathematics? And the answer is no, we're not happy. Why are mathematicians not happy with Q? Because if we try to draw the set of rational numbers in a line, then the hole has lots of holes in it. For example, √2 is not a rational number, so we would have a hole in our line at √2. Pi is not a rational number, so we would have a hole at pi. In fact, Q has infinitely many holes in it. So what do we do? What do humans do in our history? We invented new numbers. And the numbers that humans invented are called the real numbers. This is all of the numbers which can be written as a decimal. For example, 0 is a real number. I could write this as 0.0. 23 divided by 99, I could write as 0.23232323 repeating. This is a real number. And so on. Pi, I can write as 3.141592, etc. This is a real number, and so on. Root 2 is a real number. The real numbers are complete. That's a technical way of saying that if we draw all of the real numbers in a line, then there's no holes in the line. So, are we happy now? Do we have enough numbers to be able to do mathematics now? And the answer is yes. And that is the end of this week's lesson. First week's lesson was a little bit shorter than 60 minutes. Sometimes the lessons will be longer. Next week, we're going to talk about intervals, Cartesian coordinates, functions, and sigma notation. I'm now ready to answer your questions. When I get to this own slide, that means the lecture is finished, and you're welcome to ask your questions to me. If you don't have any questions, then it means you're welcome to leave.